Welcome everyone. In this video, we are going to talk about getting some of the vocabulary and relationships between some of the fundamental thermodynamics parameters. Now, in this video, we are not really going to go into what these parameters mean, but rather kind of where they come from and how they are related to each other. So, back a few chapters, we talked about intensive and extensive parameters. Remember that extensive parameters are proportional to the amount of material. And so the important ones for us are going to be entropy, volume, and number of moles. And energy. Energy is another very important one. Now, when we have two extensive parameters and we take the ratio of those, so something like mass divided by volume, it results in an intensive parameter, density. Now, we talked about in the last video how in thermodynamics we are really looking at the change that's happening. And so derivatives are what we have to be careful, what we have to use. It turns out that the derivative of an extensive parameter with respect to another extensive parameter results in an intensive parameter. And this allows us to set up three very fundamental relationships that we're going to use throughout our next discussions. So these are sort of definitions in that the temperature is the partial derivative of the energy with respect to the entropy, holding the volume and the number of moles constant. Pressure has this relationship, and mu, this is a term that we're going to learn about in another chapter or so and use a lot. This is called chemical potential. So for now, don't worry about what that means. We're going to use it and see what it means here in a little bit. But for now, it's defined as the change in the energy with respect to the number of moles, holding the entropy and the volume constant. Okay, so internal energy really is our starting point. And energy, the internal energy, which we are going to give the symbol E. Now, be careful, different books define their variables differently. Our book defines internal energy as E. Internal energy is a function of the entropy, the volume, and the number of moles. So if we wanted to find the change of energy, the dE, this is going to be equal to the derivative of the energy with respect to each variable. And so that becomes the partial of E with respect to S, holding V and N constant, ds, plus the partial of E with respect to V, holding S and N constant, dV, plus the partial of the energy with respect to N, holding S and V constant, dN. And this is what we call the total differential. Now, we have our terms that we defined, and it turns out that these terms are in our total differential. And so this allows us to make some substitutions, arriving at dE is equal to T ds minus P dV plus mu dn. And this is going to be a really key definition of how the energy changes within a system. And over time, we're going to talk about how to use this. But for now, this is a key definition for us. These are what are known as Maxwell relations. Okay, now, conjugate variables. So if you noticed back whenever in the energy, that we have dE is equal to TdS minus PdV plus mu dN. We have temperature and entropy together, and we have pressure and volume together. It turns out that these are what are known as conjugate variables. So S and T are always paired. P and V are always paired. And what we can do is, if we want to find, we have the relationship of energy with respect to entropy, volume, and moles. If we want to flop one of our variables for its conjugate there and create a new function, there is some math rules, Laplace transforms, that allow us to do this. And with the Laplace transform, it says that if we take the derivative of the energy with respect to V, holding S and N constant, it's going to be equal to negative P. Well, so if we want to switch this for its conjugate variable, it means that this is also going to switch, and it's going to be negative of its it's going to be the negative of its conjugate variable. And so the conjugate variable of P, of negative P, is going to be negative V, and we have to take the negative of that. So that gives us that the partial of the energy with respect to P is equal to V. So notice these flipped, but what is being held constant is the same. Okay, so another example. The partial of E with respect to S is equal to T. So in this case, we're not switching conjugate variables inside. We're switching conjugate variables that we are holding constant. And it turns out that we can do that without changing what this derivative is equal to. Now, okay, so let's use this. If we define a new variable known as enthalpy, and we're going to call it H, and what we are going to do is we are wanting to find the energy with respect to entropy, pressure, and number of moles, rather than volume. So we're switching this out. So we can write the total differential for entropy, where dH is the partial of H with respect to S, etc., etc. What we have here. And so now we have, these are our definitions with respect to energy. But we don't want these with respect to energy. We want H, which is an energy, with respect to S, at P, and N. So we are changing this guy. And we know from our Laplace transforms that means this is still equal to T. Now we want to take H with respect to P, holding S and N constant. And so we are changing this variable inside, which means that this is going to be equal to V. Because I've got a negative and a negative from this transform, making it a positive. Sorry about that. And so now we would take the partial of H with respect to N, holding S and V constant. So I'm not changing anything, which means that I'm not going to change anything in what this is equal to. So now I can plug these new definitions in, and I get that dH is equal to TdS plus VdP plus mu dN. So enthalpy, this is the energy of the system with changing entropy, pressure, and moles. Okay, so what if we want to change? Entropy is a hard thing to measure. So what if we want our energy term in terms of temperature, volume, and moles instead? Turns out this is what's called the Helmholtz free energy. For some unknown reason, it's given the symbol F in your book. A lot of other texts use A, but your textbook, for some reason, decides F. So the total differential, like we have done before, is dF is the partial of F with respect to T, dt, times plus the partial of F with respect to V, dV, plus the partial of F with respect to N, dN. And so now we have to work on our transforms. And so we're going to have the partial of F with respect to T, holding the same things outside constant. So we're changing the inside. And that means that the outside gets changed to the negative of the conjugate. For this one, we have the partial of F with respect to V at constant T and N. And so we're changing this outside, which means that nothing changes. And so this is going to be negative P. And here we have the partial of F with respect to N. S and V constant is also going to be mu because we didn't flop any variables for their conjugates. And so we get that dF is equal to negative S dt minus P dV plus mu dn. So it turns out that this is the Helmholtz free energy is a very useful term because temperature and volume are two things that we can really control and easily change within a system and easily measure. And so we've now created a variable that is much easier for us to work with rather than over the internal energy. And remember that each of these, because we're just transforming one variable, each of these different things are measures of energy, just using different variables. Okay, well, so now comes the complicated one, Dr. Chamberlain's favorite. It's the Gibbs free energy. And in this one, we're going to be tricky, and we are going to transform both the energy, the entropy, and the volume. And this gets us a term of the energy with respect to temperature and pressure. And it turns out that when we are doing a reaction out on the bench, temperature and pressure are the two things that are the easiest for us to control. And so Gibbs free energy becomes a very, very useful term for the energy because experimentally it's in terms of variables that we can work with. So just like the others, we have the total differential of the definition of Gibbs, and we have to work on our transforms. And so the partial of G with respect to T at constant volume and number of moles means that we are changing this inside, and so that means that the outside is the opposite conjugate. And this should be pressure. I think I made that mistake a few times. Sorry, guys. Here we have the partial of G with respect to P at constant V and N. So I'm changing the inside, which is going to give me the opposite of the outside. And so negative sign giving me a positive volume. And then the partial of G with respect to N, S comma V, is still going to be equal to mu because we haven't changed any of our variables. And so dG is going to be equal to minus S dt plus V dP plus mu dN. Okay, so here's a summary of what we just figured out. We have 4 different variables for the energy: internal energy, enthalpy, Helmholtz free energy, and Gibbs free energy. And each of these are a measure of the energy in terms of different variables. And so this gives us basically 4 equations of state that we get to use and manipulate and help tell us different things about our system. So the next video is going to be some definitions about our system, because we're going to start getting into ideas of we're doing an experiment and we need to be able to describe our system in concise language. And once we have some definitions about our system, we can start using these ideas of energy and understanding these macroscopic energy properties of our beaker of solution, or what we will start with is a beaker of water.